H is a healthy individual who has voluntarily fasted for the past 8 hours. At time 0, we draw blood from a peripheral vein to measure the venous plasma glucose concentration, here referred to as VPG. Immediately after sampling, H consumes 50 grams of glucose dissolved in water. 15 minutes later, we take another blood sample to measure the venous plasma glucose concentration. We repeat this measurement every 15 minutes over the next 3 hours, during which H continues to fast. Let's now draw a coordinate system with the x-axis representing time since glucose intake and the y-axis showing the venous plasma glucose concentration measured in both millimoles per liter and milligrams per deciliter. By plotting and connecting the obtained data points, we get a curve like this. The curve begins at some baseline value, peaks approximately 30 minutes after intake, and then gradually returns to baseline. Now the question is, how can we explain the shape of this curve? Each time we draw blood, we're measuring the glucose concentration in the cardiovascular system, here referred to as CVS. But remember, H didn't receive an injection of glucose, they drank it. When glucose is ingested, it travels through the gastrointestinal tract, which consists of a series of interconnected organs. Absorption into the cardiovascular system doesn't happen immediately. It only begins once glucose reaches the small intestine, where specialized transporters facilitate its entry into the bloodstream. This delay in transit through the gastrointestinal tract explains why the glucose concentration in the cardiovascular system peaks around 30 minutes after ingestion. Once absorbed into the cardiovascular system, glucose is distributed throughout the body and taken up by various tissues. As tissues absorb the glucose, its concentration in the cardiovascular system gradually decreases, returning toward baseline. To sum it up, glucose moves from the gastrointestinal tract into the cardiovascular system, and from there it's taken up by the body's tissues. Let's go back to H. At each step of the experiment, we drew blood to measure the venous plasma glucose concentration. From those same blood samples, we can also measure insulin levels circulating in the bloodstream. Let's draw another coordinate system. The x-axis still represents time since glucose intake, while the y-axis shows venous plasma insulin concentration expressed in both picomoles per liter and milliunits per liter. When we plot the data, the resulting curve closely resembles the glucose curve in shape. It begins at a baseline level, peaks around 60 minutes after intake, and then gradually returns to baseline. Notice that the insulin curve peaks about 30 minutes after the glucose curve. This delay indicates that insulin secretion from the pancreas is tightly linked to rising glucose levels in the blood. In fact, researchers had established this connection a long time ago, but that's a story for another time. For now, what matters is this: insulin secretion is dependent on plasma glucose concentration. So far, we've looked at glucose and insulin levels after oral ingestion of 50 grams of glucose. But what if, instead of drinking the glucose, we injected it directly into the bloodstream? Or even better, what if we could intravenously infuse glucose in such a way that it recreates the same glucose curve seen after oral intake? That would allow us to isolate the effect of the route of administration on insulin secretion. So how would we actually do that in practice? We keep the same experimental setup and begin by estimating the baseline venous plasma glucose and insulin concentrations. This time, however, we introduce glucose directly into the cardiovascular system through a second peripheral vein. We use separate IV lines for administration and sampling to avoid contaminating the results. A simple approach would be to inject 25 grams of glucose dissolved in 50 milliliters of sterile water over 30 seconds immediately after the baseline blood draw. After the injection, we continue drawing blood at regular intervals for the next 3 hours to monitor glucose and insulin concentrations over time. The resulting glucose and insulin curve would look like this. There are two key things to notice here. First, the y-axes span a wider range than those used for the oral curves. Here are the correctly scaled y-axes for comparison. Second, this setup requires frequent sampling early on due to the sharp spike and rapid decline seen in both curves. And just like with oral intake, the insulin peak follows the glucose peak, but the delay is much shorter with intravenous administration. In conclusion, this is not the outcome we're aiming for. Also, notice that we used 25 grams, not 50 grams as in the oral experiment. That's because injecting large amounts of glucose directly into the bloodstream can be dangerous and should only be performed by trained healthcare professionals. Always remember, the dose makes the poison. To truly mimic the natural glucose curve seen after oral intake, we need something more controlled than a single rapid injection. The idea is simple in theory. We need to adjust the glucose infusion rate over time to recreate the same glucose curve we saw after oral intake. In practice, this requires frequent glucose measurements and real-time adjustments to the infusion rate. Here's how it works. At time 0, we measure the venous plasma glucose concentration and set aside some blood for the insulin concentration. So far, I have shown you the glucose and insulin data as if they were analyzed during the experiment. But in reality, glucose concentration can be estimated from blood in roughly 2.5 minutes, while insulin analysis takes several hours. Suppose the measured venous plasma glucose concentration is 4.5 millimoles per liter at time 0. During the oral glucose experiment, the concentration after 15 minutes was 6.0 millimoles per liter. We now adjust an infusion pump delivering a 20% glucose solution in sterile water based on these values. This is done by feeding the current venous plasma glucose concentration, the target level for the next measurement, and other clinical factors into a computer algorithm that outputs an infusion rate. We then adjust the glucose infusion rate accordingly. After 15 minutes, we draw another blood sample to check the glucose level and set aside yet another sample for later insulin analysis. We input the updated values into the algorithm and adjust the infusion pump once more. This cycle, measure, adjust, infuse, is repeated every 15 minutes for a total duration of 3 hours. After insulin analysis, we now have both glucose and insulin curves for oral and intravenous glucose administration. Now things get interesting. Here, PO stands for per os, meaning by mouth, and IV stands for intravenous. The glucose curves are nearly identical, but the insulin curves are not. Insulin secretion is noticeably lower during the intravenous experiment, even though the glucose exposure over time is the same. In other words, the area between the two curves is non-zero, with a greater insulin response seen after oral glucose. What causes this discrepancy? Earlier, we traced glucose path through the compartments of the body during the oral experiment. With intravenous administration, the gastrointestinal tract is bypassed entirely. This must mean that something in the gastrointestinal tract enhances the insulin release that does not occur when glucose is directly administered into the blood. Researchers have identified this something as a group of hormones called incretins. One of the most studied incretins is glucagon-like peptide 1, or GLP-1. You've likely come across its analogs. They're widely used as medications for diabetes. Incretins are secreted by specialized endocrine cells scattered across the intestinal lining. Once released, they enter the bloodstream and carry out several functions, one of the most important being the enhancement of insulin secretion from pancreatic beta cells in response to oral glucose. In summary, the incretin effect refers to the phenomenon where oral glucose intake triggers a greater insulin response than intravenous glucose due to gut-derived hormones like GLP-1. The highlighted area is actually a visual representation of the incretin effect. So far, we've looked at how this effect plays out in a healthy individual, but it's almost impossible to discuss the incretin effect without touching on its role in type 2 diabetes. So, let's imagine we had done the same line of experiments in a patient with type 2 diabetes. We'll need to rescale the y-axis for the healthy glucose plot to make a fair comparison. In the diabetic glucose plot, the glucose curves shift upward and it takes longer for the glucose concentration to return to baseline after a glucose load. This reflects a reduced ability to regulate glucose levels. More importantly, the difference between the insulin responses, or essentially the incretin effect, is significantly diminished compared to what we see in a healthy person. This impaired incretin effect is a hallmark of type 2 diabetes and forms the scientific basis for treating patients with GLP-1 receptor agonists, which aim to restore or enhance this hormonal pathway. It's also worth noting that GLP-1 receptor agonists have several beneficial effects beyond insulin secretion, including weight loss, appetite regulation, and even cardiovascular protection in certain patients. So, now you know absolutely everything there is to know about the incretin effect. Just kidding, that was just the surface.